Alright, so use related rates to solve problems involving angles. So in our first example, a rocket is rising vertically at a rate of 1.5 miles per second. An observer on the ground is standing 20 miles from the rocket's launch point. How fast, in degrees per second, is the angle of elevation between the ground and the observer's line of sight of the rocket increasing when the rocket is at an elevation of 40 miles? Alright, so here we go. Let's show our rocket. Boom, boom, rocket, 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 and it's taking off, so it's definitely going to have some flames coming out of it. Alright, and then we have the ground, and then we have our little observer. And then he is watching it go up. Alright, so this is going to be a right angle here. And let's see, we can label the angle of elevation. This is going to be our theta. So let's see, our rocket is rising at 1.5 feet per second. We are 20 feet away from the launch point. And then, ground on the observer's line of sight of the rocket increasing when the rocket is at an elevation of 40 feet. Alright, so one might think, oh, here's another right triangle, so we're going to be dealing with the Pythagorean theorem. And you would be wrong, because we are dealing with angle of elevation. So we need to deal with trig functions here. So we're looking at a triangle, and we have a triangle that has an opposite side and an adjacent side. So we need to think to ourselves, what formula do we know that involves an angle, an opposite, and an adjacent side? And if you thought tangent, you would be correct. So tangent of theta is equal to the opposite side over the adjacent side. So the 40 feet is the opposite side, because that's opposite our angle, and the 20 feet is our adjacent side. So now we need to figure out what is changing. Well, as the rocket goes up, our angle of elevation increases because the observer's head is moving up. So we can rewrite this as tangent of theta of t equals, the rocket is getting higher and higher and higher, so therefore the opposite side is changing. However, the adjacent side is not changing, and we know the adjacent side is 20 feet. Alright, so I'm just going to rewrite this as tangent of theta of t is equal to 1/20th times the opposite side of t, just to show that the 1/20th is actually a coefficient. Alright, so now I'll just take the derivative of both sides. So let's see, the derivative of tangent with the theta of t on the inside means we're going to have some chain rules here. Chain rule says derivative of the outside, derivative of tangent is going to be secant squared of our inside, which is theta of t. And then we need to multiply by the derivative of the inside, so d theta over dt. And that's going to equal 1/20. And this is going to be a derivative of the opposite side all over dt. Alright, so what do we have here? Well, we have theta of t. We have the change in theta. And let's see, we have the change in the opposite side. So, what do we know? Well, the change in the opposite side is how fast the rocket is increasing, so that is 1.5. We are trying to find d theta dt. We're trying to figure out how fast the angle of elevation between the ground and the observer's sight of the rocket is increasing. No, sorry. Nix that. The rocket is increasing. So we're trying to figure out how fast the angle of elevation between the observer's line of sight and the ground is changing. So we need to find out first then what our theta of t is. And then we have to come back to our right triangle, because we know that the adjacent side is 20 and the opposite side is 40. So we know that tangent of theta is equal to the opposite, 40 over the adjacent, which is 20. So tangent of theta is equal to 2. So theta is going to be inverse tangent of 2. And then in our calculators, let's make sure that we set our mode to be in degrees. And then we just do inverse tangent of 2. And we're going to get 63.4 degrees. And now we can plug in and solve. So we're going to have secant squared of 63.4 degrees times d theta over dt, that's what we're looking for, is equal to 1 over 20 times 1.5. Alright, so then we're going to be left with secant squared of 63.4 degrees is equal to, let's see, 1 over 20 times 1.5. Is going to give us a fraction of 3 over 40. And I totally forgot to write the d theta over dt. So therefore, d theta over dt is going to be 3 over 40 all over secant squared of 63.4 degrees, which is really going to be 340 times cosine squared of 63.4 degrees, and then we can plug that in our calculator. So 3 over 40 times cosine 63.4 squared, and we're going to get an angle change of 0.015 degrees. Degrees per, what do we say, second. Alright, so now we have another example using the angle of elevation. So a hot air balloon is rising up from a level field, is tracked by a rangefinder 500 feet from the lift-off point. At the moment, the rangefinder's elevation angle is 45 degrees. The angle is increasing at a rate of 8.02 degrees per minute. How fast is the balloon rising at the moment? So just to point out here, we are dealing with degrees again. So let's draw this awful hot air balloon. Let's see how well I do here. Well, not awful, but not great. And then we say being tracked by a field tracker. I have no idea what it looks like. Let's call a field tracker a satellite. And the rangefinder, our satellite, we're calling it, is 500 feet away from the liftoff point. And let's see, theta is going to equal 45 degrees. And theta is going to be changing at 8.2 degrees per minute. And we want to know how fast the balloon is rising. Alright, so this is another case of tangent of theta equals opposite over adjacent. Alright, so again our our theta is changing, so theta of t. Our opposite side, the height of the balloon, is changing, so we have opposite of t. And this time the adjacent side is also not changing, so we'll just write that as 500. So this can be tangent of theta of t is equal to 1 over 500 times the opposite of t. Alright, so just like before, we'll take the derivative of both sides. So the derivative of tangent is secant squared. We'll leave the inside alone, then multiply by the derivative of the inside. And this is going to be 1 over 500 times the derivative of the opposite side all over derivative of t. Or with respect to t, excuse me. And actually I want to put these guys in red, so give me 1 second. Totally forgot to do that. D theta over dt, and then d opposite over dt. Alright, so what are we left with? We're left with theta of t, which we know is 45 degrees. And then we have d theta all over dt, which we know is 8.02 degrees per second. And then we are missing the change in the opposite side with respect to t, which is what we're trying to find. So in this case, we don't have to use the tangent to find our theta because we already know what that is. So then we can start plugging and chugging. So secant squared of 45 degrees times 8.02 is equal to 1 over 500 times the derivative of the opposite side with respect to t. Alright, so we can just multiply both sides by 500, so the derivative of our opposite side with respect to t is going to be equal to 500 secant squared of 45 degrees times 8.02. So this is really going to be 500 times 8.02 all over cosine squared of 45 degrees. Let's see, 500, just put this all in the calculator, 500 times 8.02 all over cosine of 45 degrees squared is going to give us the balloon is raising at a height of 8,020 feet per, what would we say here, feet per minute. Alright folks, and that is it for rates of change. This stuff is very challenging. So if you are struggling with it, don't worry, that is normal. This section is the second most challenging sections in calculus. Students typically struggle with this the second most. So please ask questions. Please come to class, and please have time with me if you aren't understanding any aspect of it. This is very difficult. Also, it is impossible to go over every single type of related rate problem that exists. So we basically covered a standard set of related rates questions, but there will be some types of questions that we hadn't go over. But hopefully, using the skills and knowledge you picked up from these questions, you'll be able to answer those. And again, if you have any questions, please let me know, and I'll see you in class next time.